All right, so let's shift gears a little bit from ceramics and talk about metals. So let's start with pure metals. So pure metals, so that is just one thing like copper, are actually extremely rare. Even things that you can buy, for example, that are copper, always have some type of impurity in them at even low levels, and so pure metals are really rare. So often we have impurities, and those impurities can go in one of two places. Those impurities, if they're similar in size, they could go in a site that would normally be occupied by the host. So copper in this example. Um, or sorry, this is nickel. So nickel is the sort of gray atoms, and then copper is the impurity in this case. And so that would go, since they're similar, then it goes into what is called a substitutional site. So basically the same site as nickel would normally occupy. So this is known as a substitutional solid solution because it's like a solution in a liquid, but just in a solid crystalline form. So it can either, so that's one place it can go. The other place it could go is in the interstitials. So this would be the case if it's a smaller impurity. So the example here would be carbon going into the interstitial sites in an iron structure. So iron is the gray here, and then you can see the orange carbon going into the small interstitial sites. So that would be if the impurity is relatively small, like carbon is. And so both of these are known as solid solutions because they form a random solution like in a liquid, but instead of there being no long range order, there is order. So carbon goes into random sites within the interstitials, or copper goes into random sites in the FCC structure of nickel. And so both of these are solid solutions, one of them substitutional, the other interstitial solid solution. So they can go into multiple places. So this is one outcome that could happen is a solution. And both of these are examples of alloys. The other option that could happen is if we add some type of impurity, or sometimes using the terminology of solutions, the solute, into the host, which is the solvent. The other outcome that could happen instead of a solid solution is actually to form a new material. So here in the background, you can kind of see that we have A and B are two different things, a gray and an orange, and you see that kind of random structure like we saw in this example. However, if A and B are quite a bit different, what can actually occur is that they form a new structure. So here you see in this little rectangle, the A's and B's have kind of aligned. And so the orange or B atoms have formed into very specific positions, and the gray as well. So they're kind of alternating in position. And so this is known as a new phase, a secondary phase, and it has a different composition, and it usually has a different structure than the solid solution that occurs. And this occurs when A and B are quite a bit different, and they form into almost like an ionic material because they're very ordered in these types of materials. And so what occurs of these kind of options, either solution or forming a new structure, a new phase, this is governed by what we call the Hume-Rothery rules. So this basically tells us if a solid solution will occur, if we will mix those two materials together and basically just get intermixing like we saw in the example here in this option, where basically the solute takes the structure of the host. So here, this would be FCC with all these either copper or nickel at random places in the structure. Same thing here. You would have iron with carbon in random interstitial places, right? So these are random solid solutions. And so the Hume-Rothery rules tell us if we're going to get that. And so these are known as conditions. In this case, we're going to limit it to substitutional solid solution. And so here's our 4 criteria for to have a substitutional solid solution. The first one being that if they're going to have a substitutional solid solution, the difference in the radii, atomic radii, between these two species is going to be less than 15% difference. So here the delta refers to difference in the radii. So that's the first rule. So basically we want them close together if they're going to occupy the same types of sites. Next is what we call proximity on the periodic table. And so we can term that as having similar electronegativities. So things that have similar electronegativities act similarly in terms of bonding. And so they occupy similar sites. 3, the solute and the solvent have the same crystal structure when they're in their pure metals. So if they have similar structures, when you blend them together, they would occupy a similar structure. And then lastly, number 4, this is the same valence. And so this is the criteria, this last one here is actually the criteria that's actually the least important. They're weighted somewhat. This one is actually the least important. But to sort of satisfy this rule, you would want the 2 materials to have the same valence. So that's the charge. However, if that isn't satisfied, then you would want to have the metal, a metal with a greater tendency to dissolve, and a metal with higher valency than one with lower valency. So there's kind of a structure here. But again, like I said, this is kind of the least important of the 4. And so we can kind of talk about 2 ways in which we can apply these. We can talk about relative, which kind of what, if we have a host material, which one will be more likely to form substitutional solid solution. Or we can talk about absolutes, where we compare 2 materials and we see if they meet all of these criteria exactly. And that would mean that we would have substitutional solid solution everywhere.